So we'll review a couple regular collisions here before we move on to two-dimensional collisions. There's something that you need to be very careful with when we look at collision problems, and that's direction. Okay, hopefully that you keyed in on that last class. When something's moving west or south, what needs to go with that number? A negative, okay? There's also a couple other ways that these problems word them to make that kind of implication, but they're not explicit about saying it. So if two objects are going toward each other, what does that have to mean about one of their velocities?
Negative.
It has to be negative, right? If one of them is moving this way, one of them is moving this way, they're moving in opposite directions, which means one of them has to be negative. Okay, so there's a couple little things that might trip you up if you're not really careful and really detail-oriented in your description of that problem, okay? So let's see here. Whoa. All right. So we have this four-term equation that we're going to use a lot. M1v1 plus M2v2 equals M1v1 prime, M2v2 prime. Okay? That equation, is it for an elastic collision or an inelastic collision? Elastic. Right? When two things end up separately, they're going to have separate velocities, which means it's an elastic collision. Okay? So let's go ahead and start writing down what we have here. M1 is 30, V1 equals to the right, so that's a positive 1 meters per second. It collides with a 20 kilogram object moving to the left, so M2 would be 20 and V2 would be negative 5, okay, because it's moving to the left. If the 20 kilogram object continues to move to the left, so that means V2 prime, right? What does the prime symbol mean? After or post-collision. Good. If it continues to move to the left with a velocity of 1.25, so negative 1.25 here, what is the velocity of the 30 kilogram object, which means we are solving for V1 prime. Okay? Any questions about where those numbers came from? Once you pick out those variables, then it's just plug and chug, right? Plug those numbers in. So 30 times 1 plus 20 times negative 5 equals 30 times V1 prime plus 20 times negative 1.25. Okay, they ended up as separate objects, so I want to make sure I use that elastic collision equation. Okay, so can we envision what's happening here? Okay, I want you to use your little hands. Okay, 30 kilogram objects moving to the right. Something's moving to the left. They both end up moving left, right? That means this one in your left hand has to have a lot more momentum, because if this guy's moving, he bumps into it, and then they both keep moving that way. Okay, can you visualize what's happening there with that collision? Okay, sometimes you got to use your little hands, to help you see what's happening here. Okay? Questions? Do we want to try an inelastic one now so we get one of each? Or do we feel pretty comfortable? Okay, so an inelastic one here. Okay, when it tells us they lock together on impact, that means they're colliding and they're sticking together, which means we need to use an inelastic equation. We only have one final velocity because now these two things are moving as one unit, which is why we just use v prime. Okay, did we get that to come out? And do we think these cars are going to be moving east or west? East, right? It started moving east. Okay, so if one's sitting stationary, one's moving east, right? There's no way that these things could start moving west. Okay, one's stationary, one's moving east. They're going to walk together and continue to move east. Did we get about 2.05? Okay, very good. I found that question that we wanted to look at, so I will pull that up here. Okay, there's no new equations that go into it. We're just now applying the concepts that we know and the equations we know to solve for things in two dimensions. So I'm talking the x direction and the y direction here. Okay, so take your time, go ahead and get this written down, and then we will start it all together as a group here in just a couple minutes. All right. So let me just kind of draw out what's happening here. You don't have to do this if you don't want to, that's fine. Our first puck has a mass of 0.5 and it's moving to the east. Our second puck is sitting at rest. Okay. After the collision, our first puck bounces over here. Okay, it goes north of east. Let me draw this a little bit. Okay, it goes north of east. So after the collision, my second puck is somewhere over, or my first puck is somewhere over here. My second puck, do we have an idea about where that might go? Do you have any sort of inkling, or where do you think it might be going after this collision if my first puck ends up north of east? So maybe this way, maybe this way, right? Do we think it's probably going to go over here? No, probably not, okay? But we can visualize that it should hopefully be going somewhere east, and we can't decide if it might be going north of east, probably going to be going south of east, okay? But I want you to have that visualization so that when you solve the problem, you can kind of check yourself to see if it's at least in the right quadrant, right? We're at least going semi in the right direction here, okay? So that's kind of an idea of what's happening here. We want to find the speed and the angle of the second puck. So we need to find out where exactly it's going after this collision. So let's start labeling what we know here. Okay, I put the first object in blue. So M1 is equal to 0.5. v1. Now, all of our velocities here, we see east and we see north. Okay, so we can't put those together, right? X and Y cannot go together. So we have to break these into X and Y components. Okay, we've done that before. We know how to break down a triangle. Luckily, this first velocity, does it have an X and a Y component? No, right? It's only moving east, so it only has that X component. So v1x is equal to 2.4, right? Because it's moving before the collision, 2.4 meters per second east, which would mean before the collision, what speed is it moving in the Y direction? 0. Yeah, 0. Okay, if I drew this vector, it would look something like this. Okay, does that vector have an X component and a Y component? No. All right. So if it helps you to draw each vector out, you're more than welcome to do so. Let's look now at the second puck before the collision. So M2 is equal to 0.3. V2x is equal to what? Yeah, 0. Why is it 0? Yeah, it's at rest. So both of these are 0. Okay, do we see why we're splitting these into X and Y? For right now, for the beginning part, it doesn't make a big difference to us. But after the collision, then we see them moving in 2 dimensions, which means we have to solve the whole problem in 2 dimensions. Okay, now let's look at post-collision. The first puck moves 1.8 meters per second at 30 degrees north of east. So we need to find v1x prime and v1y prime. Okay, how can we go about doing that? Yeah, good, right? We have to draw that vector, 1.8 meters per second. This is 30 degrees north of east. So we break that vector down into its components. So this vertical side would be v1y prime. This horizontal side would be v1x prime. Okay. These 2-dimensional collision problems require a lot of work. Okay, the math that goes into it is not that difficult, but they require a lot of work. It's going to take a lot of paper. Okay, you'll see these problems take about half a sheet of paper almost. Okay, so just brace yourself. All right, to find x, we would use cosine, and to find y, we would use sine. Please make sure that your calculator is in degrees, not radians. Do either of those components need to be negative? No. Good, because they're moving in the north direction and the east direction. Very good. Neither of those need to be negative. Okay, any questions about where any of these numbers came from? Okay, all of this was given to us in the problem. Remember, once we break down that 1.8, we don't ever use that again. Right? We're done with 1.8, 30 degrees. Okay, once we break that down, we don't use that again. So now, our goal is to find the speed and the angle of the second puck. So that means we need to solve for v2x prime and v2y prime in order to give us that final resultant vector. Okay. Questions here? All right, let's see how we get there then. Now with these problems, see how many variables we have? 10. We have 10 variables that we have to keep track of. Each with its own meaning, each with its own subscripts, right? 10 different variables. So if you don't stay organized during these problems, it's going to be trouble. Okay, so this is my method for staying organized when I do these problems. Listing all my variables very simply. And then when I start to solve in the x direction first, I usually always do x direction first. It makes no difference, right, if you do x first or y first. But when I solve it, I give myself a little kind of workspace like this. Okay? This means nothing in terms of the math that goes into the problem. This is nothing math-wise. This is to keep me organized. So this tells me right now that I'm solving momentum in the x direction. That's all that that's telling me, and that's the only reason I do that, is to keep myself organized. You don't have to draw that, okay? But you'll see me do that. So now I'm going to solve all of my x variables. Okay, the only things I'm plugging in here are the x direction, so I'm solving right now for all my momentum in the x direction. It's an elastic collision, so I use the same equation, m1 times v1 plus m2 times v2x equals m1 times v1x prime plus m2 times v2x prime. Okay, we see where these numbers came from? I'm only using my x variables right now. Okay, questions there? That is now the x component of our second puck. Okay, so we're halfway. Okay, second component of our, the x component of our second puck. Did everyone get it to come out at about 1.42? All right. Okay, so now v2y prime, we're going to solve for momentum in the y direction. So I would say py, and I would look at this one, and this one. So m1 times v1 plus m2 times v2y. Okay, my whole left side is 0 because there's no momentum before this collision in the y direction, right? One of them's at rest, one of them's moving purely east. There's no momentum yet in the y direction before the collision. After the collision, then we start breaking off and splitting up. Okay. Questions on how we got there? Is that our final answer? What's our last step here? We got to find that final velocity. Right now we have the components of our final velocity. We have to get to the last step, which is to draw our new triangle.
How did you get 1 point?
First or horizontal force? No, it makes no difference. Okay, so vertically I'm going to go south 1.5. I'm going to go east 1.42. So the velocity of my second puck is going to be the hypotenuse of that new triangle. Okay, what did we get there?
2.0.
So 2.06 meters per second at. We got to find that angle also. Good. 43.4 degrees blank of blank. One more time. Which one is it touching? East of south. Okay, and that's because it's touching the south axis, then we decide is it going east of south or west of south. Okay, so east of south. That's our final answer. Is that what we predicted? Did we predict that our second object was going to go south and east? Yeah, we did. Okay, good. This is just the almost exact same setup as the one that we just went through from the CK12 assignment. Let's try this one on your own since we just went through one like this, okay? Says it's a 7-kilogram object moving 12 meters per second east, explodes into unequal parts. It tells you the mass of one. You have to then find the mass of the other, obviously. I want you to go ahead and try this one on your own. Okay, it's just like the one we did, except now it's 2 dimensions. The reason we have to solve this in 2 dimensions is because it's east and it's south, right? Just because there's no angle here doesn't mean that it's not a 2-dimensional collision. Okay, did we get our x and our y components, or are we still working? Okay. Okay, so we would say 42 meters per second east and 37.5 north. We know they're going north and east because they're both positive. We're going to solve for that final velocity. Robbie, can you tell me what you got for your final velocity?
56.3 meters per second.
Okay. At what angle?
41.8.
41.8 degrees north of east. Did you do north of east or did you do east of north?
North of east.
Okay, perfect. So we agree 41.8 or about 42. Why do we see this one going so much faster than the other one? It's what? It's lighter. Very good. It's lighter. Okay, so because this thing didn't split into 2 equal masses, that's why the velocity ratios are kind of so far off, because we're looking at the conservation of momentum, not the conservation of velocity, right? We don't have to see an equal velocity because one of these masses is significantly lighter than the other. So that's why we can see it fly off so much faster. Okay? Okay, so let's try an inelastic one. So the difference here between an elastic and an inelastic is that we're not going to have v1x prime and v2x prime. We just have vx prime, right? We're not having to solve each of those objects' final velocities because there's only one final object. So we're dropping off quite a couple of variables here because we're not having to solve for each of those objects' final velocity components. Okay, so what's the difference between an elastic collision equation and the inelastic? What are the difference between those two sets of equations? Do we remember? What happens post-collision here? Good. The masses stick together or we add them together. Very good. Okay, so let's solve first momentum in the x direction. Okay, so final answer here should have come out to be 12 meters per second at 53 degrees north of east. Okay.